right, everybody, we are on 10 still, but still 10A. We're going to finish up. I'm going to add a few things because it's interesting. And then next week we'll do 10B. So we're calling this 10A Part 2. And remember, it's because there's so much stuff. All right. Remember, this is what we're talking about, right? The different, oh, well, I should put that on. Hold on. I thought I put it on before I left the room. Oh, can I get y'all to vote on these? These are the three different kinds of coral reefs. And if you just put a little mark by the one you like the best. And then those kids from marine biology are going to win a prize. Whoever gets first place will win a prize. So we have fringing reef, barrier reef, atoll. All right, so we're on 10A Part 2. We're going to review a little bit. We're going to talk about how light behaves. We talked about that last time. And we're going to spend most of our time talking about those other forms of light and reflection. Okay? And then next week, we're going to work almost exclusively on refraction. All right, so here we go. We have to remember that the spectrum has all this stuff, right? And we're going to see how we have low frequency waves working toward high frequency waves, long wavelengths working towards short wavelengths. There's our visible light, and our waves are something like that, which we talked about last time. Remember you ever to watch the video from last week?
I don't think I watched it all the way through, but I did watch some of it.
All right.
And I did read quite a bit. I wasn't quite sure where to read to, so I know that I read like through where it talked about the different rays and things like that.
Okay, but at the beginning of that lecture, you heard that we were changing up and spending 3 weeks. Okay, let's see if this works this way. Yeah, here we go. Let's watch a video. Oh, I gotta turn center.
All electromagnetic radiation is light. Visible light is the only part of the spectrum you can see. For all your life, your eyes have relied on this one narrow band of EM radiation to gather information about your world. Though our sun's visible light appears white, it is really the combined light of the individual rainbow colors with wavelengths ranging from violet at 380 nanometers to red at 700 nanometers. Before Isaac Newton's famed experiment in 1665, people thought that a prism somehow colored the sun's white light as it bent and spread a sunbeam. Newton disproved this idea by using two prisms. To show that white light is made up of the bands of colored light, Newton used a second prism to show that the bands of colored light combine to make white light again. Visible light contains important scientific clues that reveal hidden properties of objects throughout the universe. Minute gaps in energy at specific visible wavelengths can identify the physical condition and composition of stellar and interstellar matter. Human eyes aren't nearly sensitive enough to detect these faint peaks, but scientific instruments can. Scientists can learn the composition of an atmosphere by considering how atmospheric particles scatter visible light. Earth's atmosphere, for example, generally looks blue because it contains particles of nitrogen and oxygen, which are just the right size to scatter energy with the wavelength of blue light. When the sun is low in the sky, however, light travels through more of the atmosphere and more blue light is scattered out of the beam of sunlight before it reaches your eyes. Only the longer red and yellow wavelengths are able to pass through, often creating breathtaking sunsets. When scientists look at the sky, they don't just see blue, they see clues about the chemical composition of our atmosphere. However, visible light reveals more than just composition. As objects grow hotter, they radiate energy with a shorter wavelength, changing color before our eyes. Watch a flame shift from yellow to blue as it is adjusted to burn hotter. In the same way, the color of stellar objects tells scientists much about their temperature. Our sun produces more yellow light than any other color because of its surface temperature. If the sun's surface were cooler, say 3,000 degrees Celsius, it would look reddish, like the stars Antares and Betelgeuse. If the sun were hotter, say 12,000 degrees Celsius, it would look blue, like the star Rigel. Like all parts of the electromagnetic spectrum, visible light data can also help scientists study changes on Earth, such as assessing damage from a volcanic eruption. This NASA EO1 image combines both visible and infrared data to distinguish between snow and volcanic ash and to see vegetation more clearly. Since 1972, Images from NASA's Landsat satellite have combined visible and infrared data to allow scientists to study changes in cities, neighborhoods, forests, and farms over time. Visible light images taken by NASA's Mars landers have shown us what it would look like to stand on another planet. They have expanded our minds, our imagination, and our understanding. NASA instruments can do more than passively sense radiation. They can also actively send out electromagnetic waves to map topography. The Mars Orbiting Laser Altimeter sends a laser pulse to the surface of the planet, and sensors measure the amount of time it takes for this laser signal to return. The elapsed time allows the calculation of the distance from the satellite to the surface. As the spacecraft flies above hills, valleys, craters, and other surface features, the return time varies and provides a topographic map of the planet's surface. Back in Earth orbit, NASA's ICESat mission uses the same technique to collect data about the elevation of the polar ice sheets to help monitor changes in the amount of water stored as ice on our planet. Laser altimeters can also make unique measurements of the heights of clouds, the top of the vegetation canopy of forests, and can see the distribution of aerosols from sources such as dust storms and forest fires. Finally, visible light helps us to explore the far reaches of the universe that humans could not hope to reach physically. Using visible light, the Hubble Space Telescope has created countless images that spark our imagination, inflame our curiosity, and increase our understanding of the universe.
All right, so many uses, and for real quick, I'm going to go back to here. So many uses for all these different types, right? We're going to talk specifically about X-rays and gamma right now. Okay, so we did that, and moving on. So X-rays, high energy waves that can pass through your cells, but they make bones, teeth, and dense things more visible. Okay, so you can see some things. I used to work, at a vet clinic, and I did a lot of the X-rays, X-ray technician. And one time there was a dog that came in and had impaled itself on a fence, and it was a wooden fence, right? And so this piece of wood was up in his body. The owner told us that we couldn't see that because it had broken off or something. There was a wound, but that's all we saw. And we did an X-ray, and we couldn't see the wood very much. After staring at it for a while, we could kind of say, "Oh, I guess that's it right there," and we were able to go in and surgically remove the wood, because the wood was sort of like the same as flesh, right? It wasn't as dense as bone was. But we can definitely see, look at these hands right here with bones. Now, because this is using radiation, radiation can damage tissue, so you don't want to have a ton of X-rays taken during your lifetime, but a lot of times the trade-off is worth it because we can see something we weren't able to see beforehand. All right, but as an X-ray technician, I used to have to wear this little badge, and it would clip right here on my lab coat, and then I would wear a lead apron over, and then that little badge would hang out, and after 6 months I would have to turn the badge in and get a new one, and they would monitor to see if I was getting too much radiation. I just heard literally on the radio this morning that it doesn't matter that of technicians wearing the lead apron, that they don't need to do that. Have you ever been to the dentist? Get your teeth x-rayed like this, and you notice they say, and they make you bite on that thing that hurts like mad, right? You're going, oh, that hurts. And they said, bite down. Then they walk out of the room, and then you hear a beep, and then they come back, okay. Well, that's because they just blew some radiation into your face. And since they do it all day long, they don't want to be around the radiation all day long. And there's lead in the wall that keeps it from perforating through there. So now they're saying it doesn't matter, that the best thing for the lead apron is psychologically. And I'm like, okay, that's kind of weird. So I don't know. All right, let's watch a little video on X-rays.
In 1895, a physicist named Wilhelm Röntgen was doing experiments with a cathode tube, a glass container in which a beam of electrons lights up a fluorescent window. He had wrapped cardboard around the tube to keep the fluorescent light from escaping when something peculiar happened. Another screen outside the tube was glowing. In other words, invisible rays had passed through the cardboard. Wilhelm had no idea what those rays were, so he called them X-rays, and his discovery eventually won him a Nobel Prize. Here's what we now know was happening. When high-energy electrons in the cathode tube hit a metal component, they either got slowed down and released extra energy, or kicked off electrons from the atoms they hit, which triggered a reshuffling that again released energy. In both cases, the energy was emitted in the form of X-rays, which is a type of electromagnetic radiation with higher energy than visible light and lower energy than gamma rays. X-rays are powerful enough to fly through many kinds of matter as if they are semi-transparent, and they're particularly useful for medical applications because they can make images of organs, like bones, without harming them, although they do have a small chance of causing mutations in reproductive organs and tissues like the thyroid, which is why lead aprons are often used to block them. When X-rays interact with matter, they collide with electrons. Sometimes the X-ray transfers all of its energy to the matter and gets absorbed. Other times, it only transfers some of its energy, and the rest is scattered. The frequency of these outcomes depends on how many electrons the X-rays are likely to hit. Collisions are more likely if a material is dense, or if it's made of elements with higher atomic numbers, which means more electrons. Bones are dense and full of calcium, which has a relatively high atomic number, so they absorb X-rays pretty well. Soft tissue, on the other hand, isn't as dense and contains mostly lower atomic number elements like carbon, hydrogen, and oxygen. So more of the X-rays penetrate tissues like lungs and muscles, darkening the film. These 2D pictures are only useful up to a point though. When X-rays travel through the body, they can interact with many atoms along the path. What is recorded on the film reflects the sum of all those interactions. It's like trying to print 100 pages of a novel on a single sheet of paper. To see what's really going on, you would have to take X-ray views from many angles around the body and use them to construct an internal image. And that's something doctors do all the time in a procedure called a CT, computed tomography scan, another Nobel Prize-winning invention. Think of CT like this. With just one X-ray, you might be able to see the density change due to a solid tumor in a patient, but you wouldn't know how deep it is beneath the surface. However, if you take X-rays from multiple angles, you should be able to find the tumor's position and shape. A CT scanner works by sending a fan or cone of X-rays through a patient to an array of detectors. The X-ray beam is rotated around the patient and often also moved down the patient's body, with the X-ray source tracing a spiral trajectory. Spiral CT scans produce data that can be processed into cross-sections detailed enough to spot anatomical features, tumors, blood clots, and infections. CT scans can even detect heart disease and cavities in mummies buried thousands of years ago. So what began as Röntgen's happy accident has become a medical marvel. Hospitals and clinics now conduct over 100 million scans each year worldwide to treat diseases and save lives.
Right, there we go, X-rays. Now gamma rays, I think this might be something you're supposed to write down, yeah? Okay. It turns out that there are certain elements out there that just naturally fall apart on their own. They're called radioactive elements. And the way they fall apart, they can either send out an alpha particle, a beta particle, or a gamma ray. Also, we get these rays from the sun as well. So our atmosphere blocks most of the gamma rays, fortunately, because you're going to see alpha particle here can like burn you if it hits you, right? That's we're surrounded by a lot of radiation, but it's low-grade radiation. A beta particle can go a little farther and cause some internal damage, but the gamma ray can go right through you like a bullet. All right, so it's very, very damaging for us. It can penetrate nearly everything. Like I said, fortunately, most of the gamma rays coming from the sun are deflected by our atmosphere and the ozone layer and that kind of thing. But there are still some elements in this world found naturally that are sending off radiation in the form of a gamma ray. All right, and so when we have something like that, we can actually use it. We don't want to be exposed to it too much. It's like a little bullet shooting out of it, yeah? And so I'm going to show you here that we can utilize it medically. So this is something you're supposed to be writing down blanks for this? Alpha particle, beta particle, no?
Just the fun fact.
The fun facts? Okay. Very dangerous, can put in everything. So, here we're going to see, similar to what we saw in the video there of the guy going into the CT scan, this is a type of a scan that's using a gamma camera, they call it. And the gamma camera here is coming in. So if, for instance, we think there's a tumor, we can use this technetium, I think is what it's called, and we can inject the technetium into the patient. Now it's going to be emitting the gamma ray, so the gamma ray camera can pick that up, all right, and give us an idea of how big the tumor is, where it's located, that kind of thing. So you might think, yikes, I'm going to be putting gamma rays in my body. Well, it is very good for imaging. We can get images this way. Furthermore, they can use gamma ray beams to try to reach in there and zap the tumor. Okay, because if gamma rays kill living tissue and a tumor is made up of growing out of control tissue, a gamma ray can get in there and stop it. You see, like a little gamma ray gun. They have a very pinpoint kind of accuracy. Now, will it damage some tissue coming in? Probably. But if it's the choice between that or living with a malignant or dying with a malignant brain tumor, it might be very, very useful that way. So that's still being, developed, and I'm sure as when y'all get older, there'll be even more advances in that kind of treatment. All right, so light passes through different materials at different speeds. I believe you're supposed to write these down here. We can pass through objects. They can either be transparent, the light goes all the way through like a window, or translucent, the light comes through but not clearly. It's more like a muted window, something like that, or a stained glass window. Something, the kind of windows you might have in a bathroom that's downstairs at your house so people can't look into your bathroom while you're in there. And then we have things that are opaque. Opaque means no light comes through them at all. All right, like the wall, for instance, So then you can see right here we have transparent. Here's a window, light going right through it. Translucent, look, they used it as an example of sunglasses. Light comes through it, but not all the light, right? And we're going to talk a little more about specifics about how some sunglasses work here in a minute. And opaque, no light comes through this. So is that a backpack or something right there? Yeah, so we can see that. But also translucent, things like milk glass where it kind of distorts the light and you can't see things exactly. And also the film, maybe that goes over things. And I also always think about like stained glass windows. Those are translucent. But like even paper, right? If I hold some paper up, light will come through it, right? So you can see light comes through the paper, Or if I put a flashlight on it, that might be better. Yeah, you can see the light, yeah? Yeah. It's not as good as seeing the light through something that is completely transparent like that, right? You see it completely there. Yeah. All right. So we're going to see when light hits a surface of an object, whatever kind it is right there, these things might happen. It might just be transmitted right through it like a window, right? So that is absolute transparency, passes through. It could get reflected. Even sometimes on a transparent window we'll have light reflected off that. That if you're driving and you come across like a windshield or something and it bright shines at you, that's part of the light being reflected. It can be absorbed. The light will be absorbed into it. We'll talk about that in more detail. It can be refracted, which means to bend it and change it. It can be polarized, or it can be scattered. All right, so light's going to act different depending on what you're passing it through, like a medium through which it travels. Remember, we found out about light that it doesn't need a medium to travel through. It can go through a vacuum, it can go through space. Hallelujah, right? That's all good news. Today we're going to spend some time lab-wise on the reflected light. We'll do a little lab on that. And then next time we'll do a lab on refracted light. Okay? And so we're just going to cover these other ones really quickly. When we're looking about transmitted, right, it's just coming right through that window. Now you'll notice on this particular picture there is a little bit of light scattering going on as well, because you can see sort of this interesting cloudish shape coming around the window there, right? But that's mostly passing through and just right onto the floor. And then these parts of the window are opaque, therefore we make a shadow. Absorbed light, we have all visible light coming in. In this particular case, we have a red apple. It turns out all the wavelengths are going to be absorbed by the apple except for red. And because of that, the red is reflected, and that's why the apple's red. All right, so that's how color works. It's because this particular apple is going to absorb most of it and reflect part of it. And all color that we see, we'll spend some time next week talking about color and how it's a function of light. No light, no color is how it works. And so we'll look at that next week. So check out here, we have they look kind of like bowling balls, right? So white will reflect all the colors. Nothing will be absorbed. All right. Black will absorb all of the colors. And because think about this, hot summer day, you're wearing a black shirt. You get hotter, unless you, but if you're wearing a white shirt, that's because the light's being reflected with your white shirt. Therefore, you're not absorbing so much heat. So it says reflecting all Roy G. Biv right there. And this one right here just happens to be a red ball, right? So it's absorbing everything. Look, it takes OIG-BIV and it reflects red right there. Okay, but this will explain why wearing dark colors in the summer is hotter than wearing light colors. So, for instance, if it's a cold day and there's sun shining, wearing a black shirt and it helps you absorb some more of that warm temperature, right? I like that. You know, that on days when it's cool out, sitting in the sun, very nice. All right, now let's talk a little bit about polarized light. So polarized light is talking about the way, so this is what we're going to be talking about. We're going to watch a little video about it, about light traveling in waves. We established last time that light travels in waves and in particles, sometimes at the same time. And one thing that you would not have seen, Ren, on that was the video, because YouTube would not let me send that video about, remember y'all, about when you watched it, it did different than when you didn't watch it, going through the two slits. It was bizarre stuff. But it wouldn't let me show it to you, so sorry about that. All right, so polarized light is all about putting light in the waves in the same direction. So let's watch a little video and see what in the world I'm talking about here.
Now, you might be wondering, is light a transverse or a longitudinal wave?
Look how cool that is.
How could we test this? This device is called a polarizer. It's designed to let waves get through in only one direction. As I send the wave out, it gets through fine that way, but this way, I can't get the wave through. No matter what crazy wave I send, only the left and right components get through. It's been polarized. Now that only works on transverse waves. If it works on light, then light is a transverse wave. Because light can be polarized, we know it's a transverse wave. This is a polarizer. It's polarizing up and down. This is another polarizer. It's polarizing left and right. When these two are crossed, we get absolute darkness, zero transmittance. But if we cross them the other way, light still gets through. They're polarizing together the same way. Unpolarized light, for example, from the sun, travels to a polarizer, which polarizes it up and down. The light continues and hits another polarizer, but this polarizer is side to side. That cancels all the light. No light gets through.
All right, so it's just going through the polarizer is basically a little slotted thing that it's. Remember the little deal we looked at and saw the rainbows through it? Okay, those had little grooves cut into it that were like little miniature prisms that were cut into it. Okay, and here we're going to see that it's like these slots that it's going through, like our two-slit experiment, and it's just keeping the waves going the one direction, so when it hits the other direction, there's nothing there to go through those. All right, we've limited the number of waves of light that can come through. We use this on sunglasses. You see it cuts down the glare, so we see it's pretty sunny out here. And these are polarizing sunglasses, or polarized glasses, and they just allow some in, and it cuts down a lot on the glare. So for instance, here's with no sunglasses, and we put it on, and it kind of is a little more vibrant. Sometimes you can see even more vibrant colors when you use a polarized lens, something like that. All right, scattering light. Scattering light is basically what that first video was talking about when the light is in the atmosphere and we see blue coming through. That's because it's scattering. It turns out the scattered light waves are called Rayleigh waves, named after Lord Rayleigh, a guy who did a lot of studying on these things. I believe he's the same Rayleigh who did earthquake. We have radio waves in earthquake, so we have these kind of waves in light and in earthquake waves. I don't know that they're the same. They could be, I suppose. We're going to see scattered light causing that blue to happen. We'll watch a little video on this one.
Why is the sky blue? In the middle of a bright, sunny day, the sky is usually a shade of blue. Why blue and not purple, green, or orange? Well, it's all because of how the sun's light reaches Earth. If you see light from the sun hitting the ground, it probably looks like plain white light. However, that white light is made up of all the colors of the rainbow. You can actually separate and see all these colors if you shine sunlight through a specially shaped crystal called a prism. Light energy travels in waves, and different colors of light are created by different types of waves. For example, when our eyes recognize the color red, what we're actually seeing is long, stretched out light waves with peaks that are far apart. And when our eyes recognize the color blue, we're really seeing shorter, choppier light waves with peaks that are close together. The different colors of light are all determined by how stretched out the light waves are. Together, all the colors make up the spectrum of visible light, the light we can see. So why do we only see blue light when we look up into the sky on a sunny day? That blue color we see comes from sunlight hitting Earth's atmosphere, a layer of gases that gives us air to breathe and keeps the planet warm enough to live on. When sunlight reaches Earth's atmosphere, it is scattered in all directions by the gases in the air. The types of gases in Earth's atmosphere mostly scatter the shorter, choppier waves of blue light. So when we see a blue sky, we're really just seeing all of those blue light waves scattering in our atmosphere. But wait a minute, why is the sky a different color at sunset? Well, as the sun gets lower in the sky, its light is passing through more of the atmosphere to reach you. So even more of the blue light is scattered away before it gets to you. This allows more of the orange and yellow light to pass straight through the atmosphere and directly to your eyes. However, if the whole sky is glowing red, it could be due to particles of dust, pollution, or smoke in the air. These particles also scatter lots of blue light, which can lead to a very red sky.
All right, so it's scattering, right? So we can see here, when the sun is right overhead, when it comes down, it's scattering in such a way that we see the blue. It's like a direct angle coming, 90-degree angle or so. And then when we have sunset, look, it's scattering and the blue's kind of getting lost. And then what we see, we end up seeing red. This also will explain why the sun looks bright yellow in the day, and when it's setting, the sun itself actually looks kind of reddish, right? It gets kind of orangey red, and then going through our atmosphere scatters in such a way that we see those oranges and red. Also proof that God's a longhorn, right? Burnt orange sunset, right? No? Okay. All right, so reflection. Probably have something to write on this. When light waves bounce off an obstacle is called a reflection. We can see here our swans. Look at that beautiful reflection in the water. Some surfaces are more reflective than other surfaces. Of course, we know mirrors would be the best reflective stuff. That's why we make them the way we do. Back in the old days, we had silver on the back of a piece of glass. Now I'm not sure exactly what we do. In the really old days, like the Roman days, they would have a polished piece of metal and they would look at it and it was a little distorted, but it was the best they had, you know? And so now, like, I can see my reflection in this TV that's not lit up. If it were lit up, I couldn't see my reflection. Sometimes in a window on a day, you can see your reflection really well in a window, even though it's transparent, right? That will reflect off of there. All right, we have another video.
Imagine looking in a mirror from a sort of sideways angle and seeing a ball on the other side of the room. Now look at it represented from above in a simple diagram. Obviously, you see the ball because its reflection is visible in the mirror. We might think that we see things because our vision is looking outwards, but in fact we see things because the light is coming from the object to our eye, so we have to draw the arrows in that direction. So in our diagram, we've got two light rays. One is going to the mirror, the second one from the mirror to our eye. The first one is called the incident ray. Incident comes from Latin and means falling on. So the incident ray sort of falls on the mirror. The second is reflected off the mirror, so it's called the reflected ray. The direction the reflected ray comes off the mirror is not random. The angle it bounces off at is the same angle that the incident ray reaches the mirror with. If this is 40 degrees, this one is 40 degrees. But this is not how we usually do it when describing reflection angles. Firstly, you need to understand the word normal. It's not used here the way you might be used to. Normal comes from another Latin word that means at a right angle. Here, in this example, the normal is an imaginary line that's at a right angle to the mirror. When we talk about angles and reflection, we describe them relative to the normal. So here, you can see that our incident ray hits the mirror at an angle of 50 degrees from the normal. This is the angle of incidence. And because the ray reaches the mirror at exactly 50 degrees from the normal, it will reflect at exactly 50 degrees from the normal. This angle is called the angle of reflection. The most important thing you must learn about reflection is that the angle of incidence is always equal to the angle of reflection. It's because of this rule that all rays of light bouncing off a mirror reach your eyes in an organised way and allow you to see an object clearly. But if this is true, and it is, I promise, why doesn't every flat surface behave like a mirror? If you compare the surface of a wooden floor to a mirror, you'll notice that you don't see a clear reflection in the floor. The light rays reflecting off the mirror reach the eyes in an organised way because of the law of reflection, but the light rays reflecting from the wood floor are being scattered in different directions by the surface, giving an unclear image. And you might think the law of reflection doesn't apply to the wood, but it does. If you could zoom in really close to the surface of the wood, you'd see that it's uneven. Each ray still bounces off the bit of surface it reaches with an angle of reflection that is equal to the angle of incidence. And the result is rays bouncing off in different directions, preventing you from seeing a clear image. Very smooth surfaces, like mirrors, result in what we call specular reflection. But rough surfaces result in what is known as diffuse scattering. In both cases, the law of reflection is obeyed.
That's why mirrors are nice and smooth, right? So we can see clearly. All right, so this will be part of our lab today. We'll be looking at that. So notice our angle of incidence and our angle of reflection. They're talking about these angles, right, instead of these on this side right here. And this angle of incidence, will always equal the angle of reflection. So we have law of reflection states the angle of reflection equals the angle of incidence. That's a blank to fill in. All right, and you're supposed to draw this right here in a box somewhere. You got a box to draw that in? Yeah, go ahead and draw that. And label those parts because we're going to need that for our lab. So you see this is a plane mirror, plane meaning flat. There are also mirrors that are not flat, right? They're rounded. And they do something to the image. They change it. Either magnify it or make it smaller, depending on what you're using it for. I think I brought some of those mirrors. talk about when you look at yourself in a mirror, right? Here we are looking at ourselves in a mirror, seeing reflections. We must have light, first of all, to see anything. That makes sense. In reflection, the light bounces off an image, hits a mirror, reflects off the mirror, and enters into your eyes. Our brain interprets the light traveling in a straight line, so our brain extends the light backward, causing the image to appear, actually, if you think about it, behind the mirror. And that might sound weird to you, but think about it for a second. You're standing at, let's say you're standing at your bathroom sink, right? And the sink is between you and the mirror. And you look at the reflection. Do you see the sink too? Which way's the sink going? Back that way, and therefore you're back there. Isn't that weird to think of it that way? So we're actually back behind it. You've got the distance. In other words, the distance is evident in the mirror. You get it? Pretty cool. Kind of weird. Yeah. Oh, real quick, I wanted to talk to you about the way that lasers work. We're going to use this laser. This one I have the laser pointer a little bit today to see about scattering waves and things like that. So how does a laser work? It's kind of interesting the way it works. It takes a light and kind of, for lack of a better term, concentrates it. And it does that by sending it back and forth between two mirrors. So it reflect, boom, 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 boom against the mirrors like that. And the medium right here, the laser medium through which it passes, it typically, the way they discovered it was they found that it glowed through a particular thing called a ruby. Ruby. Do you know what a ruby is? It's a gemstone. You know what color it is?
Red.
Red. That's why it's red. Okay, because it's going through the ruby. And it's bouncing back and forth. And then this right here says partial mirror. Let's just think of it this way. It is kind of a not completely reflective mirror, but let's think of it like it has a tiny hole right there, okay? So it goes back and forth, and finally the one that has picked up a lot of light rushes through that little hole, and I end up with this light coming out like that. Now, of course, you know that there are different colored laser pointers, right? So they're using a different medium inside there, which will change the wavelength. That's all it's doing. So this particular wavelength coming off of here is going to be in the red 750 nanometer wavelength section. My husband has a really I did not bring it. It scares me a little bit. A fancy laser pointer that points a long way. And it has a purple light coming out of it. So, you know, that's the highest energy waves, right? That's the violet energy waves. So literally, we pointed it at his hand, and in seconds it burnt, it hurt. He felt the heat coming from it. So we have to be very careful. It was sold as a type of laser that will start a fire. So like if you put it down in the leaves and stuff like that, you know, so it's like a fire starter. I think we tried to start a fire with it, and we were not successful. But it scares me we keep it really high up so the children can't ever find it. Because you've always heard, don't shine a laser in somebody's eye. So this red one is going to be the lowest of the wavelengths, right? So it's going to have not as much radiative power to it. But the blue one or purple one, yikes, yeah? Then I know I had a green one as well. All right, oh, look at the kid. Yeah, he's got the laser on his right there. Okay, yeah. What is that? Is that the Incredibles? Yeah, laser on. Okay, and so also we can see what's nice about a laser is that, now you can see it hitting the ceiling right there, right? But can you see it here?
No.
You can only see it if I pass something through it. So that's because it's not scattering through this. But we're going to do a little experiment right now that's going to hopefully scatter the waves, and we'll be able to see them, okay? So it's time we're going to do our lab. So this, remember I told you to be a little shorter today, so we had time. That's why I split this into 3, so I could show those extra videos and have this time for lab. So we're going to do something similar to this, although in this third glass. So if you shine the light in some opaque material, you can see it be scattered. Some light, this is actually muddy water, and it will block the light coming through it. This is oil, but I don't like working with oil, so I didn't bring any. But supposedly I can see that beam going through the oil like that. So maybe I should have brought some more. Then we're going to do our reflection lab. It's going to look something like that. We're going to change those reflective things right there. And I did find my UV beads if y'all wanted to take some. Remember last week I wanted to do the UV beads and I couldn't find them. Well, they were in my box the whole time. So now I found them. All right, so let's get to lab.